Today we are going to talk again about an introduction to fracture mechanics, and this is part two. We had another session about 2 weeks ago where at that time we gave a general introduction. We talked about linear elastic fracture mechanics and elastic plastic fracture mechanics. We went over the FAD methodology and presented some case studies. And so today in part two, we're going to talk a little more about toughness characteristics of materials. And then we will look at crack growth assessment methodologies. And then we'll kind of go over a few of the dominant codes in the industry that are used that provide guidance for fracture mechanics assessment. And then we'll talk about inspection. And then if we have time towards the end, we'll talk about a few topics related to fracture mechanics. Okay, so before we get started, let me just give a brief introduction. My name is Daniel Ayewa. I've been with Stress Engineering Services for about 13 years and started off in our upstream business, doing a lot of drilling and production riser related work. And more recently, I work in our plant services group where I do a lot of pressure vessel related work. And you know, the great thing about fracture mechanics is that it bridges all of those fields, both the upstream, the midstream, and the downstream aspects of our industries. Okay, so let's get right into the topic. Today we're going to talk about toughness. We'll start by talking about toughness properties in materials. So fracture toughness measures a material's resistance to fracture when a crack is present. Now, if you recall in part one, we discussed how the stress intensity factor is an important measure of the conditions at the crack tip. And so as the load increases, the stress intensity increases. Well, the limit of that load is the critical stress intensity factor, which is effectively the fracture toughness of the component. Now, fracture toughness varies quite widely across different materials. You know, the plot on the right shows toughness on the horizontal axis with strength on the vertical axis. And you can see, you know, various materials used in engineering. Glasses obviously have relatively high strength, but very low toughness. And you know, many of you may have experienced this if you've ever dropped your cell phone. Glass has a fracture toughness of about 1 KSI squared of inch, so it's relatively brittle material. But on the other end of the spectrum, we have metals and metal alloys, which are both high strength and high toughness. And as a result of that, they are excellent engineering materials and, you know, used a lot in the industry. Okay. So while metals are generally on the high end of the toughness spectrum, within themselves, they show a relatively broad range of toughness values, and this is often reflected in their failure modes. You know, on the one end of the spectrum, we have ductile failures, and ductile failures are characterized by a significant amount of energy absorbed. You know, we have the elastic regime, and then a lot of yielding and plasticity occurs before final failure. And you might recall that the area under the curve of a stress strain curve is an indication of the toughness. So here we have a fracture surface for some connecting rods that were from a failure analysis at our labs showing kind of a ductile failure on the surface. So ductile failure typically occurs by microvoid nucleation within the material. These microvoids then begin to grow, and eventually they link up and coalesce, and that forms the crack. So this whole process of microvoid nucleation involves a lot of energy absorption, and so these materials present as tough. On the other end of the spectrum, we have brittle failure, which you know, the image on the right, you might recall from the frac stack we looked at you know, in part one. So the failure nucleates at some point and then it quickly propagates through the material. The stress strain curve shows a lot less plastic deformation. The area under the curve is much lower. And so these cleavage fractures don't really absorb a lot of energy. They can be very sudden and catastrophic in nature. So brittle fracture occurs by cleavage along specific crystallographic planes within the metal structure. So you're actually breaking bonds here in order for cleavage to occur. And cleavage is actually influenced by the presence of multiple second phase inclusion particles within the microstructure, which can serve as very local stress risers and you know, create stresses high enough to break the metal bonds and induce a cleavage fracture. Okay, so let's talk about carbon steels for a moment and the ductile to brittle transition behavior. So in general, carbon steels have this ductile to brittle transition behavior whereby they transition from high toughness on the upper shelf to lower toughness on the lower shelf. The lower shelf is characterized by cleavage fracture, as we talked about previously, and on the upper shelf, it's characterized by a lot of ductile fracture and a lot of ductility. And so the transition follows a trend like a hyperbolic tangent curve, and you know the reference temperature, which is approximately a line going through this transition, the temperature at which the transition occurs is an indication of the toughness of the material. And so if you can imagine a material operating at a given temperature, if the transition, let's say at ambient temperature at 70 degrees, if the transition temperature occurs at high temperatures, then you know the material shows its lower shelf, and so it appears to be low toughness. Whereas if the transition occurs at lower temperatures, then you know the operations see the upper shelf behavior, and it shows as a kind of a ductile materials. Okay, so it turns out that transition curves for different heats of materials are similar to one another. So for a given heat of material, the transition curve can be established through Sharpie testing. And various heats of material all have different transition curves. So when the transition curves are indexed to a reference temperature, they collapse into a common trend. Okay. So some influencing factors as far as the transition temperature include the loading rate, the operating temperature, we've got environmental factors, and then the material composition as well. So the image shows a series of Sharpie tests ranging from kind of lower shelf behavior to high upper shelf ductile behavior. On the lower shelf here, you can see the cleavage fracture. There's not a lot of deformation in the material. As you progress higher and higher, more and more ductility. This kind of shiny area in the center is cleavage fracture, and on the edges you have a more ductile behavior occurring with void nucleation and growth and coalescence as we discussed before. Okay, the transition zone obviously is in the middle between those two, where both mechanisms occur. And in general, within that transition region, ductile failure may initially occur, but then all of a sudden a critical inclusion is encountered, which leads to cleavage fracture, and then you have that cleavage that occurs in the center. Okay. So in general, within the transition region, as a result of this mechanism, there's a high degree of scatter in the measured toughness because it kind of is based on the probability of sampling a critical inclusion that induces cleavage. All right, so how do we determine fracture toughness? So in general, mechanical testing is a great way to determine fracture toughness. We have ASTM standards that provide guidance on material sizing and the geometry of the test specimens to achieve a valid test. So common shapes include this single edge bend specimen here, and then also the compact tension specimen. So in general, when performing these tests, samples are pre-cracked using fatigue in order to produce a sharp crack at the tip and to get a true measure of the fracture toughness. And so when testing, the load is steadily increased until the specimen fails while measuring the crack mouth opening displacement. And if effectively at the end of the day, you can determine K1C, CTOD, or J1C values depending on the nature of the fracture. It's also possible to generate toughness resistance curves. So the critical fracture occurs at the onset of crack propagation, and if it's unstable, it's kind of a single event. Whereas if it's a ductile material, it might just be the onset of a tearing type behavior with increasing toughness as the tearing progresses. So here's a test setup for conducting a fracture toughness test on a compact specimen. Again, we're applying loads and tension, and we can see a gauge clip for measuring the opening displacement. And this is a similar test. This one was conducted at the test labs here at Stress Engineering with a bending specimen. So it's a 3-point bending setup, and the gauge clip is also measuring the crack opening. Okay, and this is the fracture surface after separating the two pieces. You can kind of see the fatigue pre-crack that developed that was used to pre-crack the specimen before the actual loading. Okay, so that's mechanical testing. We can also determine fracture toughness based on Sharpie tests. Now, the Sharpie V-notch impact energy is not a measure of fracture toughness, but it's kind of a quick and easy test. It's a qualitative test that can be used for quality assurance, and it provides an indication of the toughness. And so it's become widely used in the industry, and correlations exist to convert between the Sharpie energy and toughness values. Okay. So it's possible also to use a series of K1C estimation methods that are available in API 579. And these generally start by establishing a reference temperature for the material, kind of a Sharpie reference temperature. And then from there, we have a number of material databases that contain information about the toughness of materials, which we'll talk about over the next few slides here. All right, so let's talk about determining the reference temperature. So this is a transition curve based on Sharpie tests, actual Sharpie tests that were performed. And the reference temperature can be determined by performing a hyperbolic tangent fit to the data. And we often refer to the 20 foot-pound transition temperature as the reference point. So in this case, it's about 48 degrees Fahrenheit. It's also possible to get an equivalent transition curve based on ASME exemption curves. So in general, ASME categorizes pressure vessel steels into exemption curves A, B, C, and D with increasing toughness. And so if you look at each of these curves, you'll see that curve A has a transition temperature that's approximately 88 degrees. That's the highest one. And curve B has a transition temperature of about 50 degrees. Okay, so by understanding these transition temperatures, it's possible to get and to estimate an equivalent kind of reference temperature that can be used for Sharpie correlations. So once we have these reference temperatures, we can there are a number of methods we can use to determine toughness. The first is the ASME lower bound curve. Now this curve is kind of an older data set that's based on a series of Sharpie tests and some drop weight test methods. And so, researchers collected all this data, all this transition data from these materials and indexed them to their reference temperature. And of course, all these curves collapse into a single curve. You'll notice that the x-axis here is the reference temperature, the operating temperature minus the reference temperature. Okay. And then, if you look at these curves at lower temperatures, the toughness values are much lower, and then as the temperature increases, the toughness values increase. So we have two curves here. One is the fracture toughness K1C curve, which is based on quasi-static tests, and then the K1R curve is based on dynamic tests. Okay, so at a given temperature, you generally have lower toughnesses based on the dynamic test. And then the cutoff temperature is set at about 100, the cutoff toughness is set at 100 KSI root inch for steels with unknown chemistry, and 200 for kind of more modern low toughness steels and low sulfur steels. And so sulfur actually represents an element within the steel microstructure that tends to form those inclusions that we refer to as potentially causing and initiating cleavage fracture. So let's look at a quick example. Say we're operating at 77 degrees Fahrenheit. We have curve B material. So the reference temperature is 50 degrees Fahrenheit. So our T minus Tref is 27 degrees Fahrenheit. And if we look on this curve at 27 degrees and we trace it up, we hit just under 75 KSI root inch. So that's a 69 KSI root inch. So this is kind of a lower bound toughness. Another means of estimating the toughness from the transition curve is based on the master curve, the toughness master curve, which is a similar but a more recent data set. It's based on actual fracture toughness measurements. And so the curve is indexed to a slightly different value, T naught, which can be estimated from Tref. And one thing to note is that the reference temperature from a Sharpie test differs from the conditions from a quasi-static fracture toughness test. And because dynamic tests kind of present themselves as slightly less tough, there's actually effectively a shift between the Tref from a Sharpie test and the T naught from an actual fracture toughness test. Okay. And so the K1C is then evaluated and it can be adjusted based on a length parameter. And so for a material with a yield strength of 38 KSI and we have a T naught of minus 27 degrees when it's operating at 77 degrees Fahrenheit. And that gives us a median fracture toughness of 220 KSI root inch, which when length adjusted gets us to 161 KSI root inch. Now, one interesting thing about the master curve is that it captures the statistical nature of cleavage fracture in the transition region, and it does so using a normal distribution, which basically describes the likelihood of encountering one of these inclusions within the microstructure. And so if we look at the median, upper bound, and lower bound fracture toughness values, we see that the values vary quite a bit. We have 161 as the median, 93 as the 5% lower bound, and obviously you can get higher than that. So typically in fitness of service assessments, we're trying to look for the lower bound behavior, but it's useful to keep in mind that the actual behavior of a given component can occur anywhere in this range. Okay, so that's a brief introduction to toughness properties and how these can be estimated in carbon steels. So let's switch gears a little bit, and we're going to talk about crack growth assessments now. All right, so in engineering systems, fatigue crack growth occurs in systems that are subject to cyclic loading. So examples include mechanical fatigue in production riser systems. This is due to the action of the vessel motions and the waves and the wind. So what we have here is at the top of the production riser, you might have a titanium stress joint. So these components see a lot of fatigue. In pipelines, fatigues may be due to pressure fluctuations from the contents inside the pipeline. And then in pressure vessels, we have this pressure cycling for any number of reasons. For example, this pressure swing absorber sees multiple cycles of pressure periodically. And we also have thermal loading, which can lead to fatigue, for example, in coke drums. And we often have cracks on skirts in certain areas that are as a result of the normal operating cycles of these components. Okay. Other reasons for crack growth include environmental reasons such as stress, corrosion, cracking. We have hydrogen cracking and subcritical crack growth. And so any of these could lead to crack growth. But in general, we're going to focus on the mechanical reasons for crack growth and fatigue. So when we think about the fatigue life of a component in cyclic service, there's potentially a long period where the component undergoes a crack initiation, and this may vary from component to component, from 5 to 80% of the life of the component, and is influenced by things like the loading and the stress concentrations and the quality of the weld in the component. And at some point, a crack nucleates and begins to grow. And at this point, fatigue crack growth comes into play, which we're going to talk about today. And as the growth of the crack progresses, eventually it becomes large enough that it becomes critical and you have a final failure. So the total of this spectrum is the SN fatigue life. Okay, and you might recall from the last presentation we talked about a failure in a component that failed by fatigue loading. This was the rotor disc of a steam turbine, and you can clearly see that the crack has grown over time. Okay, so fatigue damage depends on the cyclic loading stress range, which is the difference between the minimum and the maximum load in a given cycle. There's also the concept of the R ratio, which is the ratio of the minimum to the maximum, and gives an indication of whether the cycling is occurring at high stress values, that would be a high R ratio, or at lower stress values. Okay, so we're probably very familiar with fatigue life being described using an SN curve, and that's the relationship there in terms of fatigue. Well, if we think about fracture mechanics, the analogy is that, instead of stresses, we have the stress intensity factor. And so the same cycles result in a minimum and a maximum K value. And the crack growth depends on delta K, which is the difference between those two. And we also have an R ratio there as well. Okay. Now recall that the relationship between K1 and sigma is shown here. This is a linear relationship between the stress intensity and the stress. Okay, so crack growth assessments consider this delta K value and related to the change in stresses as well, using a similar equation. The Paris-Erdogan law relates delta K, which is the stress intensity factor range, to the crack growth per cycle. And that's this power law relationship right here, where the ADN is the incremental crack growth per cycle, and C and M are constants that depend on factors such as the material and the environment. And delta K, again, is a stress intensity factor range. So this is a plot of a DADN curve. You can see delta K occurring on the horizontal axis and DADN on the vertical. In general, the Paris law region is this linear portion at the center of the curve. And if you think about a crack growth progressing, it may start at a lower delta K value. Since delta K depends both on the stresses and the size of the crack, it will tend to progress to the right as the crack grows. And so the rate of crack growth increases with time. Okay. If we take the power relationship and we take the log of both sides, we see that it is indeed a linear relationship with a slope on the curve and an intercept. And if we combine these two equations, the DADN and the delta K equation, we can estimate the fatigue growth, crack growth life by taking the integral of both sides. And of course, A varies over the course. The size of the crack is changing as the crack progresses, and so you have to take the integral there. Okay. Now, below a certain threshold, delta K, the crack growth does not occur. This threshold K value occurs at much lower stresses. But as crack growth approaches this third region, then it accelerates and moves to failure as it approaches the critical K value here. Okay, so let's look at crack growth constants in general and their behavior. They're not very sensitive to material properties within the Paris law region and within a given material system. So, the codes typically have a single crack growth curve for steels of different strength and different properties, and that doesn't really change too much. It does change, and it is, however, affected by the influence of corrosive environments, which can accelerate the crack growth. And it's also influenced by the R ratio, in some metals more than others. For example, in steel, the steel and air curves are shown on the right here. We talk about R ratio greater than 0.5 and less than 0.5 as generally the same, whereas in other systems like titanium, it varies a bit more continuously over a range of values. And then we also have the concept of the mean and the design curves. So in general, the mean curve represents kind of a more average value based on actual measurements, and the design curve represents kind of the upper bound crack growth rate, and making it more useful for design cases in general. And these constants are available in the ASME and BS 7910 codes that are used for that provide guidance on fracture mechanics assessments. Okay, so let's take a look at a quick example here. So the geometry we're concerned about is a cylindrical shell. It has an internal surface elliptical crack right there. The shell diameter is about 20 inches and the wall thickness is 4 inches. So we're going to assume a stress concentration factor of 0. In general, stress concentration factors increase the stress range and hence the stress intensity range. And then we're going to consider an initial flaw size of 2 inches long and 0.2 inches deep. This initial flaw size may represent a flaw detected in the field on an operating piece of equipment, or it may reflect just an allowable flaw size during design, a detectable flaw size. Okay, so yeah, so we have, we're using steel and air. We're using the design curves, assuming a fracture toughness of 100 KSI root inch, and we're applying cyclic stresses of 25 KSI. So this is a full pressure depressure cycle, and one every 2 hours. So that's about 4,000 cycles a year. Okay. So in general, when we evaluate these results, the fatigue assessment begins with a FAD assessment of the initial flaw size, and we see that that falls squarely on the inside of the FAD boundary. As we grow the crack, the ADN, it's getting larger and larger. The crack progresses towards the boundary of the FAD. And while the crack is progressing, we're performing periodic FAD checks based on some extreme load. In the case of this full reversal cycle, the extreme load is just the maximum stress. In other systems, it could be some extreme event that might occur. So failure is determined as the crack growth when it eventually intersects with the FAD, and the resulting number of cycles represents the crack growth fatigue life of the component. Okay, so we can look at these results in terms of the progression of the crack depth and length with cycles. And again, this is based on a known flaw that we described before. So what we find is that the critical flaw depth is about 3.26 inch and at about 65,000 cycles. And these results can be used to assess design fatigue life of a component, or for remaining life assessment, again, for an existing component with the flaw detected in it. And these fitness for service or design criteria typically include some margin to failure from what is actually calculated on these curves. So for example, in ASME Section 8, Division 3, which is a pressure vessel code, they consider fracture mechanics, and it requires the lesser of half the number of cycles to the critical flaw size. So in this case, that would be 32,600 cycles. And then it also considers the number of cycles required to grow the crack either a quarter of the way through the wall or the quarter of the critical crack depth. And in this case, that's 34,000 cycles. So between the two, clearly this criterion is the controlling one. Another way to present results is to perform an offset from the critical flaw size curve. And this offset represents the number of fatigue cycles, represents fatigue cycles based on some interval. So in this case, we consider a full year of cycling, and we can produce, as a result of the crack growth assessment for multiple aspect ratios of cracks, we can produce this offset. And what that tells us is that this is the allowable flaw size today that will go critical after a year of full reversal cycles. And again, this is the design curve. If we look at the mean curve, we see that that allowable size becomes a little bit larger because the mean curve represents a slightly slower crack growth. So it has a larger allowable. Okay. This is a great way to present results when you are just looking for inspection criteria. Maybe you're performing some manufacturing and you want to look at inspection criteria for a component that is going to be in fatigue service. And again, for in-service components, it's useful for inspections because, again, you can compare these curves and set them as acceptance criteria for a given inspection interval. So the interval within which you can kind of take the equipment down and inspect again for crack growth. Okay. All right, so that's an introduction to crack growth assessments. Let's talk about some of the codes that are applicable for both design and fitness for service methodologies. So one of the premier codes that we look at in the field of fracture mechanics is API 579, Part 9. It's primarily a fitness for service code. And Part 9 covers assessment of crack-like flaws. We also have BS 7910, which is a code that is focused on fracture mechanics as well, from BSI. And these two really represent the primary codes that cover the methodology and the practice of fracture mechanics assessments. A few additional code references in the pipeline world. We have API 1104, welding of pipelines and related facilities, and they have an Annex A, which provides guidance for using fracture mechanics to establish acceptance criteria for pipelines, and it references BS 7910. And then, as mentioned previously, we have Section 8, Division 3, Article KD4, which uses fracture mechanics for design of Div 3 pressure vessels. So just looking at some of the methodologies that are employed by these codes, we've covered a fair bit of topics in between Part 1 and Part 2, talking about fracture mechanics. And so really these code methodologies identify these topics and apply them for different levels of assessment fracture mechanics. So API 579 part level 1 uses a series of screening curves, and the curves are available for a limited set of geometries. These are pre-calculated curves that can be used to establish the maximum length of allowable length of a flaw. And these lengths are typically based on two discrete depths. There's a 1/4 T flaw, and then there's a through wall crack, which is a 1 T depth. So the solid line represents the 1/4 T flaw, and the dashed lines are the 1 T flaw. And by the way, this chart specifically is for cylinder longitudinal joint with a crack-like flaw parallel to the joint. So there's a similar chart for different geometries. And then the curves also consider the material condition. So curve A typically represents the base metal, and the B curve represents a weld metal that has been post-weld heat treated, and the C curve without post-weld heat treat. And so it's really handy to be able to pull up one of these charts if you're an inspector in the field and you detect a surface crack of a given length, and you can roughly characterize it based on a 1/4 T or a 1 T depth. Then you can go in the field and establish what the maximum length is and evaluate your flaw. So the way that the toughness is captured is using the reference temperature. So if you look at the bottom axis here, we see that the reference temperature, which we previously discussed is an indication of the toughness, can be used to, based on the operating temperature and the reference temperature of the component, you can position it on the horizontal axis here. And these reference temperatures are available in tables in API 579. So for example, that previous example, we looked at 38 KSI yield strength, and we found curve A has a reference temperature of 88 and curve B 50. So again, these are tabulated and kind of easy to use. Okay, so next we move on to level 2 assessment, and BS 7910 also option 1. Both of these use a FAD assessment methodology and perform an engineering critical assessment, which considers failure due to fracture as well as plastic collapse. So at the end of the day, we can end up with critical crack size curves and failure assessment diagrams evaluating these components. In general, it takes a little bit more work. It requires a more detailed knowledge of the material properties, the K1C. You can use the various estimation techniques that we talked about previously for establishing that. And then in addition to that, the codes provide selected appendices that tell us what to assume for the residual stress in a weld, for example, and help us to estimate material properties. And then also both BS 7910 and API 579 have the reference stress solutions included. Okay, and then we move on to kind of level 3 or option 2, option 3, BS 7910, more advanced techniques. In 579, level 3 is required when crack growth is possible, and that uses the Paris law that we just discussed briefly. A few other level 3 techniques include, starting with a level 2 FAD, but based on actual material properties. So that modifies the shape of the FAD a little bit and provides a more accurate result. We can also do a level 2 analysis based on stresses determined from FEA of an uncracked geometry. So we get the stress profile at certain locations where it's not possible to estimate based on simple code calculations, and then we apply that to a FAD-based methodology. And then even further, we can perform FEA with a crack geometry where we model the crack explicitly and we determine K or J values from actual loading of the geometry. It's also possible to establish a J-based FAD using FEA methodologies. Okay, and finally, these codes talk about ductile tearing analysis, which is a combination of the FAD and a JR curve, which captures the behavior of crack growth in ductile materials beyond the initial crack propagation. Okay, so these are codes. Let's talk finally about detecting cracks. Let's talk about inspection techniques. So in general, inspectors find indications, and if an indication is larger than a predefined size, it's considered a defect or flaw. And if it's sharp, then it's a crack. So a lot of times what we see during inspection, it's important to establish or determine whether it truly is a crack, because that makes a difference as to how you evaluate it and the risk of failure. So inspection objectives include to locate and characterize these flaws, determine if they're crack-like, the size of the flaw, length, height, position, and then their orientation relative to the principal stresses in the component. Okay, and we can evaluate the results of these inspections based on critical crack sizes or based on allowable flaw sizes if they are in fatigue service. And so each inspection method has its own accuracy, and that should be accounted for when doing assessments related to fracture mechanics. And in general, when we inspect cracks, we don't find nice, clean, elliptical flaws. I mean, sometimes we do like in a fatigue type flaw that I showed previously, but oftentimes you'll find multiple cracks. And so it's often necessary to recharacterize the flaw, and the codes provide guidance for doing so based on spacing and proximity. It might require you to treat both flaws as a single crack, and then also based on reorientation of the cracks to establish an equivalent crack that can be used for assessment. Okay, so let's talk about inspection techniques. We have surface techniques such as magnetic particle testing. This is useful for ferromagnetic materials, and it's based on the principle that magnetic fields tend to concentrate on sharp edges, and so we can use that to detect flaws and cracks because the magnetic particles will tend to concentrate on those regions. Also have liquid penetrant testing. This one is based on the fact that you place a low surface tension liquid which is able to seep into the cracks, and then you put a developer on the surface, and it pulls this liquid out and indicates the location of the crack. So these are surface techniques, and these are great for determining the length of the crack and for using level 1 methodologies, for example, to evaluate the cracks. We also have volumetric techniques such as ultrasonic testing. That can be shear wave or angle beam testing, and it can also be phased array testing. These use ultrasound and the reflections from ultrasound in the specimen to detect the presence of crack and also to size the cracks. And so, these techniques are always advancing and provide a great means for evaluating flaws. We also have radiographic testing. This is basically an X-ray image of the component. This is often done on brand new pressure vessels to detect the presence of flaws. Time of flight diffraction is another ultrasonic method based on the diffraction of sound around the crack tip. It can be used for sizing cracks as well. And then we have acoustic emissions testing. So I'll talk about AET for a moment. This is a service provided by Stress in general. And AET is based on the principle that active damage mechanisms at the crack tip emit sound at a certain frequency. And so if you can place sensors all over the vessel, you can detect these sounds and use them to, first of all, establish the presence of active crack growth, and also to triangulate and to locate the cracks. So oftentimes they install a waveguide on the surface of the component, which can be applied through insulation and various other things, just to provide contact with the vessels and transmit the sound out to the sensors. So typically when the AET occurs, you need to load the vessel in some way, either by cyclic loading in its normal operating conditions, or by going maybe 10% higher than its normal operating pressure, so that you can excite those cracks and identify where they are located. So various characteristics, it can be applied while the component is in service, it doesn't need the removal of insulation. So from that point of view, it can be convenient to do. Global coverage, you can evaluate the entire vessel in one go and identify where cracks are active for various reasons. It can't size the crack, so when you locate the crack by various means, you then need to kind of go back and use other NDE methodologies to accurately identify and size the crack. But AE represents cost savings because it allows you to focus inspection. So for example, a flaw like this, which just has, it's an ugly looking weld, but there's nothing necessarily sharp here, and it may not even light up at all in AET, and might just be fine. Okay. So a few related topics. I know we're kind of getting low on time, but let's see if we can get through these very quickly. The first one I'll talk about is auto-refrig brittle fracture. This occurs in carbon and low alloy steels as a result of significant cooling to lower shelf toughness properties. Now, we talked about that transition that can occur in carbon steels. Oftentimes what happens is that the pressure vessel operates at ambient temperatures and is fine, has adequate toughness, but then suddenly experiences some cooling event like an auto refrigeration, or it can also be from ambient temperature that cools it to lower shelf toughness while it's still under load. And that can lead to a very sudden fracture, like this, for example. This is a pressure heat exchanger where it got very cold and the shell effectively just shattered. And so the way that we prevent against brittle fracture is by setting a minimum allowable temperature, which again is based on those Sharpie exemption curves, and can also be determined using more advanced techniques such as FEA and fracture mechanics. So in general, as long as the vessel temperature remains above the MAT, the vessel is safe. And finally, it's possible to inspect. So in general, we assume that such a fracture would occur from an existing flaw, and it's possible to inspect the vessel to prove out that there is no flaw larger or less than this size. So if you're interested in this topic, there's another webinar on by my colleague Kanan on auto-refrig brittle fracture, and we both work in this area and can provide kind of general guidance on that in general. And finally, I'd like to talk briefly about ductile fast fracture, which can occur at pipelines. The method for addressing this is the Battelle two-curve method. The first curve captures the velocity of the crack. As you can see, at higher pressure, the velocity increases. As the pressure decreases, eventually it's low enough that the crack will not propagate. On the other hand, you have a decompression that occurs, from some initial crack, and the decompression progresses through the pipeline at the speed of sound. So again, the crack velocity depends on the toughness or the Sharpie V-notch energy and the wall thickness of the component. And the decompression wave velocity depends on the speed of sound in the liquid and the operating temperature. And so when you're up here where the decompression velocity of the liquid, of the contents is very high, then it quickly propagates away from ahead of the crack much faster than the crack can grow. And as a result of that, you don't see too much damage. But on the other hand, okay, so briefly, this is a curve that represents fracture velocity and the decompression curve for ethane. Ethane operating in a 12-inch pipeline. Okay, so again, as you can see, as the toughness increases, you get more and more distance from the decompression curves, which is a good thing. But again, on the other hand, if at this lower pressure where the fracture velocity can be higher than the decompression velocity, what ends up happening is that as the crack initially propagates, the decompression wave maintains a high pressure behind the crack tip and drives it continuously until, and it can run for miles. So you end up with a picture like this. So this is ductile fast fracture in pipelines. So again, these are two related topics to fracture mechanics, to the field of fracture mechanics. And with that, I think we can conclude in general. So we talked about toughness properties and how they can be measured or estimated. We talked about crack growth assessment and how it relates to traditional fatigue methodologies. We talked about codes and methodologies, and this basically marks the end of our two-part presentation. So in general, the field of fracture mechanics is relatively broad and sometimes complex, and stress engineering is ready to partner with you in understanding these problems. And at this time, I will take any questions.